Hi, my name is Brent Sergent. I'm an associate data scientist with MPH, and I'm going to be giving a high-level overview of a couple of our data science tools and how we produce them. So before we begin, I'm going to start by answering a couple of preliminary questions, namely, what are data science tools and why do we create them? So if a data scientist is an individual that derives insight or knowledge from datasets to the benefit of the requester, then a data science tool is any application that assists that data scientist in that process by either cleaning the data or performing analysis on it. We create these tools in order to call upon previous work which has already been verified, allowing us to be more efficient. We also create these tools to allow our teammates to utilize them, learn from them, and expand upon them, which allows us to create a collaborative team of problem solvers with greater problem-solving potential. So now I'm going to derail for a moment and talk about coal mining. And I know what you're thinking, what in the world does coal mining have to do with data science tools? Well, it turns out there's actually some interesting lessons we can learn from it and apply to our development of these tools. So prior to the 20th century, coal was moved out of mines using carts and tracks. These heavy carts would have to be manually pushed by individuals out of the mines, which was labor-intensive and expensive work. So along comes Richard Sutcliffe, and he realizes this. And he notices that he could take this relatively new invention at the time, the conveyor belt, and tweak it such that it could survive in the environment of these mines and carry the coal out, eliminating that labor-intensive work. Not only would it do that, but he would also make the mining less expensive by making his conveyor belt able to be packed up and transferred from site to site, whereas the carts and tracks were very site-specific and often left behind once a mine was exhausted. So, lessons to learn from this. One, there's no reason to reinvent the wheel. There already are many applications and tools that have already been created before us that we can use to form the base of our project. Next, we want to make our tool adaptable. The more places it can be used, the more likely it will be used to eliminate extra work. Finally, our tool must be easier and more efficient for the user. No one goes to Home Depot to find a tool that will make their job more difficult. In the same sense, we want to make our tool such that people are willing to seek it out by making it as desirable as possible, which is done by meeting these two descriptions. All right, now I'm going to go over each of the projects. There are two of them that will be covered in this presentation, the Aegis Geocoder and the Data Quality Completeness Report. So with that said, I'm going to start with the Aegis Geocoder, and I'm going to give a little bit of background behind the scene that led to its development. So you can imagine that in your state, you have a project where events occur, and you want to record the location of those events. These locations may come across in your data set like addresses and look something like this, relatively uniform and consistent. Or perhaps not even like that, but like this, where if we took that pinpoint away, it would be hard to decipher where the original location was. That is where our tool comes into play. We want it to take these addresses and compile it into a list and send them through our tool such that the best possible guesses come out. But not just that, but all the relevant information associated with it, such as the spatial data, the latitude, the longitude, or columns like the city and county name. Essentially, we want to put the pinpoint back on the map such that the data can be used in map applications like Tableau, or such that it can be easily combined with other data sets. Now, at first you might be thinking, well, that sounds like a massive undertaking. And you would be right, except recall back to our coal mining example, where Richard Sutcliffe used a tool that already existed, which did most of the work, but had to be modified. Well, that is what we're going to do here. It turns out that the GIO office has a geocoding API that does most of this work for us. So, what is an API? API stands for Application Programming Interface. This interface allows us to communicate with another computer and request it to complete calculations on data we send it that it has been programmed to perform. APIs come with documentation that tells us how to format data using a programming language such as Python or JavaScript. Good documentation is crucial for a good API. Poor documentation essentially makes a useless one. So you may be thinking, what is the purpose of our tool if the API already does all this work for us? The answer is that the API can handle only so much data per request. It wasn't made to handle hundreds or hundreds of thousands of records. That is where our tool comes in. It essentially acts as the throttle, constantly formatting the addresses from the list, sending them off, and then storing the results. For the GIO Office's API, Python is the programming language that is utilized. Python is well known for its less rigid rules as well as being easier to grasp compared to other programming languages, which is why it is one of my favorites. Despite this, we should still develop our code such that the following attributes are met. One, our code should be readable. There are coding standards such as PEP8 that exist for this purpose. Once a coding standard is chosen, it should be kept and followed throughout the entire application. You should also include comments in your code. Comments are lines of code that the computer ignores, which allows you to write whatever you want for people to come in behind you to easily understand what a block of code is doing. Two, the code should account for human error to a degree. Humans are unpredictable and they could do a lot to mess up your tool. So you can't provide an error message to every specific thing that they've done wrong, but you can write some general notes to help guide them in the right path. Three, the code should be formatted for possible future expansion. We could make the most condensed and efficient single line of code spanning hundreds of characters and utilizing rare functions. But then no one would come in behind and expand upon it, and it will be discarded when it needs to be updated. Finally, our code should be reusable. We want to make our application such that it be callable from other application. This product's environment includes the following libraries which were made with that purpose in mind. Time, which is a function that can time is a library which has a function that allows you to delay processing for a given period of time. Pandas, which is very good for structuring data frames. NumPy, which is good for statistical calculations. And finally, multiprocessing, which allows you to perform multiple calculations at once. The original data set that I was given for this application was formatted with 4 columns, being the street address, city, state, and zip code columns like you see here. Not all the cells were filled out in every column. Some of this information wasn't complete. Some columns contain data that it really shouldn't have. Per the API's documentation, I could send it as it was, specifying the columns by their address components. However, since it wasn't consistent, I decided to lump them all together into a single line, which looks something like this, which also was acceptable per the API's documentation. And I passed that through in chunks to the API, and once that was done, I had my first working version of this tool. So now I'm going to go over some of the general improvements which were made to the application, making it more efficient, which if you recall per our coal mining example, one of the attributes we want our tool to have was making it more attractive to the users by being more efficient. So the first thing I did was implement that multi-processing function I mentioned earlier, which allowed me to send multiple addresses to the API at once. However, with larger datasets, I ended up overwhelming the API by sending too much information and had to implement that time function to delay the application for periods of times when this occurred to allow the server to reset. Then if a dataset was passed that contained both useful address information and non, I allowed the application to save off that non-address information and add it back to the end with the results. And then finally, I added a couple of error messages, such as when no address information was passed or when the user had incorrect credentials. So, end result of this was the code was stored on a repository to be called upon in various data pipelines, allowing for better automation since now thousands of records can be sent through using the script. This allowed us to obtain valuable spatial information, which allowed our data to be linked back to other data sets and be used in other mapping applications, effectively putting that pin back on the map. Now we're going to go over the data quality completeness report. And just like in our previous project, I'm going to give a little bit of background about the scene that led up to its development. So recall back to our previous example where we had a data set where some columns were more filled out than others. The idea behind this tool was to make it a table output that contained what percent of each of those columns were not null or not empty string values. This seemed relatively easy enough, so we decided to make a couple additional calculations that could also provide us more insight into the completeness of our data sets. The first thing we did was we decided that there were 3 data types that were worth focusing in on. These data types were strings, dates, and numbers. The additional calculations for strings, or as we ended up calling them, categorical columns, were to display the top 5 most reoccurring values and how many times they reoccurred. For numeric columns, we decided to calculate statistical values relevant to them, such as the mean and median. And finally, for categorical columns, we decided to record the number of records associated with each year in the dataset. Some hurdles we initially had to overcome were large datasets needing more memory than was available. In order to bypass this, we had to implement a sampling option. We also allowed the user to utilize a YAML file, which is a file that is used for configuring scripts like this. In order to allow a user to run a single calculation over a specified column in case they wanted to run over the entire column for a large data set, allowing the memory to be directed to that column. Identifying the data types was also a challenge initially, but we decided to bypass doing this in the script and use the data types that were listed in the database using the systable. Finally, we implemented a multi-processing function again to have multiple calculations to occur at once. This tool gave us an output which looks something like this, where the data quality schema gave 4 tables, 3 associated to each data type and their respective calculations, and 1 with the overall completeness score. So to give you an idea of what a table looked like if we opened one up, you would see columns like this, the table name, column name, schema name, and the respective calculations in each columns. Additional information such as when it was written to the table were also recorded. Whenever a table is ran, the results would append to these tables if the calculations associated with them were requested. If there were none, say for the numeric column, or there were no numeric columns, then nothing would be written to that table. This made our tool adaptable to whatever distribution of data types that table had, which again was one of those lessons we learned from our coal mining example. So again, we're just going to go over some error catching and improvements. First thing was to account for human errors such as incorrect credentials or maybe an invalid schema name or invalid table name. And so we had to do that and give out the appropriate error messages. Then we added a log file, which passed when calculations for columns were complete and at what time, so you could understand where the application was. Then to the YAML file, we added domain inputs, which allowed a user to run a calculation over a certain range of values. And finally, we added some Easter egg functions, such as if a column contained over a certain threshold of zip code or county names, then the column would be flagged for that calculation. However, these will probably be moved to another script in the data quality pipeline that we're working on. So, end results of this was an output that gave us a synopsis of the dataset. It allowed us to identify what columns were mostly filled out, what might be mostly useful, and it also allowed us to catch errors in reporting, such as if there was a drop in the completion percent over a period of time or a recent update to that data set showed a drop in that completion percent, then we could go in and investigate. And that concludes this presentation. Please feel free to reach out to the data science team at MPH for any questions, comments, or concerns. Thank you for tuning in.